Hello, good morning. My name is Dan Daly. I'm a senior principal engineer at Intel. Today I am going to do my best to substitute for Nuru Sundar, who couldn't make it this morning. And also a lot of this content was put together with Yadong Li. We all work together on the architecture team for the different Ethernet products within Intel. So I'm going to start talking about IPU usages and SPDK. And you might be like, wait, I just walked into the DPU section of SNIA here. So I'm going to talk a little bit about probably why we call it an IPU. And I think some of that came through in the previous session. The question about multi-tenant resource isolation is a big part of why we call these devices infrastructure processing units, is because we treat these as infrastructure that is meant to be isolated from the workload. And this is for security and efficiency purposes. So we'll talk a little bit about those usages up front. And then we're going to talk a little bit about the things that we're doing in SPDK to make this work better. So a lot of what we're doing inside of the IPU is we're taking how SPDK is used today in a server where everything is sort of co-located. We're migrating that functionality out of the server into the infrastructure. And then we want SPDK to be able to effectively support both of those sort of deployment scenarios very seamlessly. We're going to talk about the SMA, which is an API used to configure things. It's very similar to the OPI storage API that we talked about in the previous session. And then we'll talk a little bit about how SPDK, IPDK, and OPI all fit together. It's a ton of acronyms, and it's super confusing. So, but these are all complementary pieces that we're going to give you the map of the world there. All right. So let's start with usages. So maybe the first order bit here is that we're doing block storage offload in these IPUs. So at some point, we will likely move into sort of higher level storage protocols about file and object store. But going back to the reason for being for these IPUs is that you look back at where they were needed, the infrastructure providers who are doing infrastructure as a service. We'll keep hitting this word infrastructure. I swear it doesn't stand for, the I is for infrastructure, not for Intel. These infrastructure providers had tenants who wanted to offer their customers a virtual disk. And they wanted that virtual disk to be SSD fast so that that customer didn't feel like they were giving something away by virtualizing their workload. And they wanted to be able to strictly rate limit that disk so that the customer couldn't buy a slow disk and then just blast data into that virtual device. So these usages are all about providing that virtual disk to that customer and enforcing security, QoS on that device, and then making that device resilient so that that storage information can follow the application as it moves around in the cloud. And so all of these different usages that I'm going to go through, that is the core functionality of this usage, is this little floating disk that I am making certain guarantees about its performance. The expectations are extremely clear between the infrastructure provider and the customer. And these different usages here are either different components to provide that infrastructure, or just different approaches to be able to get to that same end. So the first use case that we're going to talk about is NVMe over Fabric. So NVMe over Fabric, y'all know this better than I do, actually, but we use the built-in NVMe over Fabric functionality in SPDK to be able to make it easier to demonstrate that virtual disk functionality in the open source. So when we are offering that virtual disk to the tenant and the tenant goes and does a write, we take that operation, that request, please write this data. In SPDK, we wrap it up in a packet and we ship it over a protocol. And SPDK offers lots of different protocols, but the one that we have been testing and validating is NVMe over Fabric, NVMe over TCP, depending on your network requirements. And this is very powerful because it allows you to have the diskless model for these tenants. So I don't need to, when I land my tenant on a server, also go and unplug a bunch of disks and plug it into that same server. I'm going to take those virtual disks, I'm going to carry their requests, reads and writes and flushes off of where they're running and put it to where their data is stored. And the way I get from A to B is very custom in this environment. If you ask, well, what protocol does your customer run? They actually usually don't run NVMe over Fabric, but NVMe over Fabric is a great example of how you go from A to B and make that data resilient, so you never lose a bit. So we'll go through that usage in the next slide. Another use case is to be able to take local storage and move it into, and just move it off the system. So this is sort of I would call it the SaaS replacement. Maybe I am not offering storage to a tenant, but I kind of just don't want to have all of those disks sitting on that server in the event that server crashes or that server just can't hold all of those disks in one place. I can disaggregate that and move it into a different place. It's really similar to what we do with a JBOF. And so an IPU can also be helpful in terms of, instead of having direct cables from your PCI to your JBOF, we can use an IPU to be able to take those virtual requests that could be on bare metal or in a VM or on a container and place it into the bunch of disks that are attached over the network. And in the last case, I'm going to talk about the SPDK usage of where SPDK is in both the initiator and the target. In OPI and also in IPDK, which I'll talk about in a bit, we talk a lot about IPUs and DPUs on the initiator side, where we need to provide that tenant isolation, we need to provide that security, that QoS, all of that virtualization functionality happens in the IPU and the DPU. So that's why we sort of focus on that. But on the other side, the target technology is, I would say, IPU and DPU are optional. You can decide whether or not you want to use use an existing target with an IPU. Do you want to build a new target that uses IPU as the SoC, or do you want to have the IPU as a coprocessor inside of your target? So I'll talk about that usage as well, and how we are trying to bring everyone along by injecting the work that we do into SPDK, so that if you're sort of ready to adopt these new devices, that you don't have to go and change the software environment that you're in. If you're already using SPDK, it makes it really easy to almost have these different devices almost be like a choice in, in NIC, or a choice in network adapter. Okay. So let's talk about the NVMe software stack. So inside of SPDK, you have both sides of NVMe. If NVMe is sort of a virtual wire between the user and the disk, then SPDK provides the capability to take those requests, pop it into a packet, send it over the network, resend it over the network if it fails, or flow control, waiting for the network to be ready, taking that packet, removing the packet headers, and putting that request into a disk. And it also has capabilities to do things like encrypting that data as it goes across the network, and decrypting it when it returns back to the user, so that your data is encrypted at rest. So when it's in the disk, it's sitting there encrypted until the user's ready to read it back out. And so this is a great thing to have for DPUs and IPUs, in terms of this has already been worked out for a core-based or server-based solution. And so the change that we want to make within SPDK is just to be able to allow it to support these different form factors, where we're going to let the IPU provide that isolation between the user and the infrastructure. And then on the target side, we can use the DPU and IPU to provide that end-to-end resilient networking function, so that you can have lots of different initiators talk to an individual target. And so, probably the simplest example is if you just had SPDK running in a server and it's got a ton of disks. We're going to put as many disks as possible in the system, and then allow different initiators from different places access that target and be able to get to their virtual controllers and their virtual disks. And this is something that you can set up today with server of your own, disks of your own. You don't need to necessarily have someone set it up for you. And this is really powerful. So this allows you to say, all right, well, now I can look to see what are the benefits of the CPU, the compute architecture on that target. What are the benefits of the different accelerators on that target, to compare the different types of performance and the different security guarantees that you get from what's on that platform. And we can the control point of all of that can be built right on top of SPDK. On the other side is where IPUs began, is on the initiator side. Like I was saying before, sorry for the extremely tiny picture on the right, but on the other side, where the user has some virtual disks, you can offer a disk, let's say, to a Kubernetes cluster, and that Kubernetes cluster can request the size. They can have the disk be already pre-made with their data already loaded onto it, and we can attach that disk virtually into their environment. And then CSI can come and provide each container with the storage that they need. And then what happens on the IPU is that each individual disk is hardware separated. So even if that means that very difficult for someone to try to look at someone else's disk if they don't have access. And the logic of serving that disk is separate from the host. It's not even resident in the same system. So you have that hardware separation, and in the case of IPU, you also have hardware QoS. So if and we'll show a demo of this in the next session, 2 sessions from now, is that if one of these disks is starting to have either using too much bandwidth, so it's taking up too much of the network on the network side, will be rate limited. Essentially, the request response process will be slowed to rate limit it to its pre-agreed upon bandwidth limit. And you can also set an IOPS limit, so that if they're doing too many requests within a given time, in hardware, you'll rate limit that function so that they can't overwhelm the infrastructure sitting behind. And so that all of that happens in the IPU, and it is sort of logically hardware offloading functions that used to live in the infrastructure, moving it into that IPU device, and having it be much more secure than where you have to write this in software, and potentially write this in software on the same system as the tenant. And to kind of walk through the flow of that arrow there is what happens is that when that disk does that operation, we have inside the IPU something called MPI transport. And what that is doing is it is presenting to SPDK the raw read or write flush request, putting it into a queue so that SPDK on the software side, now this is actually happening in the ARM cores on our, in the ARM cores of our E2000 IPU, or in the Xeon cores in our FPGA-based IPU. It's the same function, where these cores are load balancing across a set of queues to be able to fairly service each of these different requests that are coming over that transport bus, applying their own level of security on those requests, packaging them into an SPDK BDEV, and then using SPDK to packetize on the network side. They're also reacting to any sort of flow control or transport functions on the network side. So in the case of TCP, you're running the standard TCP stack from Linux on the cores of the IPU. Or if you're running RDMA, you're using the RDMA function of the NIC on the network side. And that's to go from top to bottom. And then you reverse that coming in the opposite direction. So in the opposite direction, as the responses come back, you pull the packet out of the transport, flow control or retransmit if needed, to get that full response back. Inside the BDEV layer is where that response is held inside SPDK. And then we go back in the MPI transport layer, and we're going to say, all right, we'll have a response for you. It'll go and put it directly into memory on the host side, so that there's nothing in the host that's facilitating that function other than the driver. So then we hand that response directly to the context, whether it's a container or a VM or a virtual function or just the plain host. Drop it into memory and tell the driver that the response is ready for the user. And when we have this SPDK integration, it makes it simpler to adopt these new technologies. So the Intel IPU E2000 has a code name Mount Evans. It is a 200 gigabit capable IPU. And it uses this MPI transport function in conjunction with SPDK to be able to implement this initiator. Now, you can say, this is everything that I want, and I don't need anything more. But really what this has been developed for is for you to be able to say, all right, well, I already have an initiator. It may be based on SPDK, it may not. But this code here in the open source is the example of how you can take your existing initiator, block storage initiator solution and adopt the E2000. And what the feedback here has been very positive because we've sort of tried to package up all of that hardware offload because what is being offloaded here is actually the storage initiator code. We're not doing anything specific to the host. Actually, the host's experience is unchanged, except for a lot more performance. But in terms of who is the target audience for this, it's you here at the Storage Developer Conference. We're trying to make it easier for a storage developer to adopt this type of IPU, both E2000 and our FPGA-based IPU, and we make that easier by using standard APIs and basing it around SPDK. And so when we're in that environment inside SPDK, our goal is to ease that adoption and be able to best demonstrate these benefits of an IPU. So we've started with this MPI transport layer. This is, inside your code, what you'll see is that instead of doing something like a vhost or a VFIO user to be pushing and pulling things out of memory, you use the MPI transport to just configure that function in the IPU, and the IPU handles it. So there's no cores running on the IPU to do that host side memory operations. And we do that, and that's how you get the hardware-based isolation. We've also adopted SMA as a way to configure the logic on the initiator side. So SMA is exactly what you would expect it to be. Things like create controller for NVMe, create a disk, and that create a disk can be NVMe or BirdIO block or BirdIO SCSI. Set the rate limit for that device. Connect that device to the BDEV so that can get tied into your transport protocol. So all of these functions are sort of exactly how you expect it to be. And we took SMA and we also used it to develop the OPI storage APIs. So in a later session, we'll talk about it's the same functions that we did in SMA. We're going to demonstrate those with the OPI storage APIs, which are very, very similar, but have a different transport. They run over gRPC, and so you'll see those functions in action. One of those functions that I think was talked about in the earlier session is multipath, is the ability to be able to take multiple paths through the network and have those be redundant paths in the case of network failure. And that requires some amount of configuration on both the initiator and target side. And so we'll demonstrate that in a little bit. Looking forward, there's a lot of things that in, I would say, production, initiator and target pairs for block storage that we want to continue to add into the open source. And we're particularly keen on these functions because we have hardware blocks in the IPU that can offload these functions. Compression is a great example of, depending on the size of your blocks, doing compression in band can be extremely valuable and is common in different deployments. Another function that we will demonstrate later today is crypto. I mentioned about being able to have your data be encrypted before it lands into the disk and decrypted as it comes out. That's a function that is in SPDK today, and we want to sort of make that more standard across the different vendor implementations. There are also a set of really interesting storage-specific offloads that these accelerators can provide to, in this case, you're offloading the cores that are on the IPU DPU. So that's proven to be pretty valuable. If you start to get to the point, just like Joe said earlier, where you're not only doing storage, but you're doing networking, you're doing Kubernetes, you're doing microservices offload all on that IPU. If you can reduce the number of cores needed for storage, you grow more space to be able to use that infrastructure device for more services. All right, so I talked a little bit about SMA. And so the way that this works is that in IPDK and in SPDK, we have examples of how you can, from a config driver or directly from Kubernetes, you can invoke SMA to be able to create a disk, set its size, set its rate limit, set up those virtual disks, and determine how they are shared on the device. We have, inside IPDK, we have support for this in previous release, and we have also moved to the OPI APIs. Like I said, they're very similar. I think it's good to just take a 1 minute and do the decoder ring of all these different technologies and acronyms. So for the storage recipes that we have, for today's purposes, SPDK is the most important technology. It's been an important technology for block storage for the last 5 to 7 years, and it will continue to be so. And Intel is very, very committed to this technology. This is enabling these technologies on our CPUs, on our IPUs, and inside of networks that contain Intel components and software. What we're doing with IPDK is we're trying to be able to take all the components from storage, all the components from networking, bring in the different crypto elements, and make sure that they can all be built together on the same system. Getting back to that same value prop of it is really important to be able to use these IPUs for more than just one thing. And then OPI is the parent of IPDK. And if you think of IPDK as an implementation of OPI, OPI is where most of the vendors in this space, most of the vendors presenting this week in the space of DPUs and IPUs have all come together to agree on the interfaces and the processes that you would use to adopt this technology. So we want to make it possible that someday you could say, I don't just want to adopt Intel's IPU or Marvell's DPU. I would like to be able to say, I want to adopt an OPI compatible device, knowing that the APIs and the processes that I'm going to invest in are going to be consistent across all these different types of vendors, and even within a vendor, there are different implementations. So these are how these pieces sort of layer together, SPDK being the core, IPDK being an implementation of a broader solution, and OPI being that focus on consistency across different vendors and implementations. And to talk a bit about, in more detail, IPDK, is that IPDK has not just storage, but networking and crypto for infrastructure as a service. That's where these products started. But we've quickly seen that all of the same values that we had in infrastructure as a service with cloud service providers, all those values still apply when you go into a private cloud or into enterprise or into your own deployment, where you want to have isolation between infrastructure and your workload, and you want to be able to finally control how your workload consumes those infrastructure pieces, and be able to evolve your infrastructure separately from your workload's lifecycle. And so we've done a couple different releases of IPDK. We're on 2307 today. Our next release will be 2401. And in 2301, we released a new recipe that deals with Kubernetes. So we're offloading the network of Kubernetes, and within storage, we'll also start to tie that together so that your networking, storage, and crypto of Kubernetes can all be offloaded with an IPU. I think I talked about this before, but IPDK and OPI are effectively the same project. And IPDK has its own release cadence as a sort of a complete solution in of its own. But any API, any BKM that is defined in OPI and agreed upon, IPDK will follow, so that you can use IPDK as a tested, validated implementation of the OPI APIs and provisioning mechanisms that we define in OPI. And like I said before, how SPDK is core to everything that we do in storage is that when we run IPDK, you'll see that for the storage recipe, you'll kind of say, why do I need IPDK? This just looks like exactly what SPDK is doing, and that's by design. We didn't want to reinvent the wheel. We wanted to make sure that if you were already familiar with SPDK, but maybe you're running it on a host, that when you brought up IPDK and you started running it, you'd say, this looks just like my host, except there are these little extra interfaces for accessing the hardware offloads that are inside the IPU. And we'll get into these examples a little later in terms of a demo of the different functions that we offer today in OPI security. So in summary, I think what I said earlier is that SPDK is not just the ideal framework for IPUs and DPUs, it's the framework. It's the core of what we use. It will, of course, go and tie into parts of the kernel, tie into other parts of a platform. But what we wanted to do is to be able to tie in the the lower level functions of what an IPU does so that you can logically think about, all right, when I'm adopting this IPU, I am moving the function that used to be on the server, putting it onto the IPU, and all the things that used to run in a core now run in an IPU core, and now I can offload functions that are now sitting in that IPU environment one by one, whether it's tenant isolation, crypto, compression, transport, RDMA. One by one, I have a standard interface via SPDK to go and take advantage of those features. And I would say that as a storage developer here, you say, well, I'm interested to be able to take my solution, my application, on the initiator or the target side. I want to go and try this out. I want to go and run this on a DPU IPU, and I want to see the benefit. And our goal as vendors is to enable you to make that as easy as possible. And our goal within OPI is to have that be as standard as possible. So you don't feel like you have to go and sign on the dotted line with your vendor and be stuck with the design choices of any particular implementation. So we absolutely encourage you to go spdk.io, OPI, IPDK. The code is out there, and we demonstrated that you can get it up and running pretty quickly. So with that, I'll stop and flash this up for 2 seconds, and then go back and ask for questions or comments or that anyone may have. Jump to this slide. Yeah. Mm-hmm. The question is, on the target side, what kind of scale have you tested? There's a different presentation on the different scales for the different IPUs. But it's pretty simple in that the IPUs were designed to be line rate. So to be able to fill that, that pipe, in the case of both of our IPU implementations is 200 gigabit, different 2x100, 1x200, 4x50, whatever. And so the design point is to be able to utilize all of that bandwidth, either all for storage or a mixture of storage and networking. And so those are all important use cases that these implementations are required to meet. Yes. So I would reference each of the IPU implementations for their own performance data, but they do have that. Yep. Yeah, good.
The configuration on the right.
Mm-hmm. The configuration on the right is really north-south, where I'm using the PCIe there is just sort of fan out, and then all of the data is going from a disk into the IPU or vice versa. So the IPU is a root complex in this case. It's like it is the SoC. Yeah, in that case. Yeah, in that case, I'm sorry. Yeah, in this case, we're using the storage server effectively as fan out for that for those disks. Yeah. Now, the storage server can also be used to run certain protocols within the target. So as opposed to a JBOF, which is very simple, the storage server will also do things like triple replication, erasure coding, things like that. And so that is much more than just fan out. So that's really the difference between the right-hand side and the left-hand side, and the rightmost and the one beside it. Yeah, there. Yeah. Yes. Right. That's right. Yeah, the question was how do maybe APIs like one API or CUDA or other APIs, let's say for a different type of accelerator, how do they coexist with these APIs for infrastructure offload? And for GPUs specifically, I think Joe mentioned it a little bit, is that the GPU APIs almost layer on top. That's something that we use the infrastructure to virtualize. So and that's because someone using one API is more akin to someone using a virtual disk than is the person who is programming the infrastructure. These are often two different people. Now you could say someone in the infrastructure wants to use a GPU to, let's say, do inline inference on one of these devices. That's still something that we keep relatively separate. So if we can keep I would say if we are successful in, just for these infrastructure offload functions, being able to come to a common API across all these different vendors, that's a big achievement. And then these other accelerators for different functions, I think it still makes a lot of sense to treat them at the virtualization layer. Mm-hmm. Storage acceleration should absolutely fall underneath OPI, and that's absolutely something that things like offloading the CRC, offloading the hash, compression, these are things that we want to go and explore inside of OPI and have a standard way to do those. Yeah. Yes. Yeah, so I think within SPDK, let's take compression for an example. We've been using the DPDK compression APIs as effectively the standard that a lot of different vendors are falling underneath. The similar things are happening with like CRC and hash functions. Again, we're going back to DPDK as the place where we can best agree on what are the interfaces to go and program those functions. Yeah. So,
From a point of view, do you consider like other topics like offloading the events
within SPDK, there's a couple different transports that are supported. TCP, RDMA. I think if we wanted to go and see how InfiniBand could be supported, SPDK would be the right place to do that. Within OPI and IPDK, we haven't. We sort of float above that design point. But and again, it really points to the concept that this SPDK code and the things that we put in IPDK are a great starting point for you to be able to get things up and running quickly, and then be able to say, all right, well, this looks like my design, but actually I use InfiniBand, and I need erasure coding, and I need this type of security applied. So it's a great starting point for that type of development. Yeah.
Very interested in taking some of these APIs and actually pushing it into a standard so that you can actually code for other processors that are out there besides Intel. Some of us sell other stuff too. So
Absolutely.
any interest or desire from Intel to collaborate with some of the other
Yep, so for storage, we've actually done that. So it's Intel, Marvell, NVIDIA, AMD, a couple others. We have come to a storage API that we all pretty much agree upon, and that's within the OPI context. And so we'll show in a later presentation how we got there. And if we need to come and take that agreement that we've arrived to, bring it to SNIA or bring it to some other context, we would absolutely do that. But today we can demonstrate that commonality across 4 or 5 vendors with code that we have today.
So today you have an informal agreement. You don't have this.
Agreed. Yep. And so, yeah, absolutely TBD. If someone came in and said, "I will," this is what you need for broader adoption, we'll do that. I don't think there's anyone who say, no, we wouldn't do that. So, and that's why we're here today, is to have people be aware of OPI and the progress that we've made. Say, hey, we need the standard to get there. Yeah. The question was on the left-hand side, do you see a use case for accelerating cloud storage?
Yeah. The cloud storage is slower and is lower require storage more.
Mm-hmm. Yeah, so we have done performance tests where we have compared a virtual disk hanging off an IPU being attached to some number of targets in the network. And we've compared that to a directly attached SSD on that same host. And we've found that the performance difference is very, very small. And that's because most storage operations are relatively large for a network, 4 kilobytes, let's say. And the network at the bottom has gotten so fast that the latency to get across that network, the latency to go through all these different stages is still smaller than the latency on the disk on the other side. So if done correctly, if you're looking at all of these different stages, an IPU where these functions are in hardware can reduce that latency further to the point where you could offer to your customers a cloud SSD or an SSD that just so happens to be diskless and not directly attached. It becomes difficult to that end customer. They don't feel like they've given anything up in exchange. Now you could do it the wrong way and performance can be bad, but we've absolutely looked at and it's a design requirement for that virtual disk to look exactly like a disk of a particular size, performance, and bandwidth. Yeah. Smack. Yeah, the question was, do you have a framework for managing the QoS at each disk? Framework, no. API, yes. So we have an API for you to be able to isolate each of the different devices, hardware isolate the devices, and then set the amount of IOPS and bandwidth that each device can handle. And then inside of SPDK across the network, you can set the QoS to determine sort of how your storage traffic goes across the network, and within that storage network traffic, how you what kind of traffic classes you put on that system. Now, again, this is going back to the idea that this is a starting point for your solution, where it gives you all the touch points to be able to get the right things in hardware to get all those latencies really low. And then you can put on top your framework that would invoke those APIs to be able to have that fine-grained control. Yeah. Absolutely, 100%. I would say not within OPI, but certainly broader within the community, SPDK especially. There's use cases there. Yeah. All right. Thank you.